And okay, for experiment 8, oxidation reduction reactions, what is happening, we had a single displacement reaction is actually oxidation reduction reaction. So in general, you know what is happening. Activity series you already know about from experiment 7, which is involved in the oxidation reduction reaction. You are using, or your reference to the activity series to determine if the reaction is going to take place or not for single displacement reaction. There are other types of oxidation reduction reactions, like combustion reaction. Combustion meaning an element combining with oxygen. So combustion of gasoline, which is a hydrocarbon, is made of carbon and hydrogen. Carbon will generate carbon dioxide, hydrogen would generate H2O, water. Each of the elements is combining with oxygen. That's like a type of oxidation reduction reaction. By definition, what is called oxidation? Can you tell me what is oxidation? Oxidation.
Increase oxidation state.
Increase in oxidation states, very good. And what is going to happen to an element to increase the oxidation state? Basically, it's going to be loss of electron, right? Electrons are lost. When the electrons are lost, the number of protons is going to be greater than number of electrons. So just going back, like basic stuff that you all know, yeah, all elements, when they are in the periodic table, they have same number of electrons and number of protons. Now, if the element gains electron or loses electron, is going to gain charge. Electrons carry negative charge, so loss of electron is going to end up with a balance of positive charge. So if 2 electron is lost, there would be 2 positive charge. If you have an ion that has 2+ charge, losing additional electron is going to change that to ion with 3+ charge. So for every electron lost, the oxidation state is going to increase by 1. So loss of electron, increase in oxidation number, or the last one definition for oxidation would be gaining of oxygen, is known as oxidation. It defines as oxidation. Now, reduction, what would be reduction then? What happens in reduction?
You gain electrons.
Gain of electron, okay. So, and then synonym to that, or same definitions, just different different way of saying, if the element gains electron, is going to gain negative charge, or oxidation number decreases, right? So decrease in oxidation number, gain of electron, or loss of oxygen is going to define as the reduction. When there is oxidation in a reaction, reduction also takes place, because we don't generate electricity. It's not electrochemistry, it's just a reaction, oxidation reduction reaction. In electrochemistry, when there's a chemical reactions that you actually remove the electron to use it as electricity to turn on light bulb or so, that's different. In this case, you are going to the reaction is going to generate electron, or one element is losing electron, another element is gaining electron. So oxidation and reduction goes together. So that's why it's known also as a redox reaction, oxidation reduction reaction. One is gaining electron, the other one is losing electron. You already know the the activity says some of the elements that they are more willing to lose electron, others are willing to gain electron. If the element is providing electron or losing electron, it provides electron to something else to be reduced, so it's also known as a reducing agent. So something that is being oxidized is acting as reducing agent. If it's being reduced, what it means is gaining electron, so it's kind of pulls electron from something else, and it's going to cause that something else to be oxidized. So if element is being reduced, that is known also, has another definition of oxidizing the agent, because it's pulling electron or is helping something else, another element, to lose electron. Oxidation number, there are a set of rules that you are using to find oxidation number. We want to make sure that any element in free state, that means the way they appear in nature, like oxygen gas, oxidation number is 0. But if the oxygen is combined with any other elements, then the oxidation number is not 0, it's a different number. Chlorine gas, that's how it appears in nature. Aluminum, Al, that's how it appears in nature, is an aluminum solid and is 0. A compound has the total number of oxidation number for a compound is 0. And the ions, if you have the ions, oxidation number equals the charge of the ion. There are some that you fixed number for oxidation, assigned number. Some elements, they could have more than one oxidation number, like nitrogen in this example could have an oxidation number of 3 or 5, or 3 or 5 or 1, and you can just find out in the compound by setting up equation and trying to find the oxidation number based on what is attached to nitrogen. If you have an NO and nitrogen monoxide, for nitrogen monoxide, you have one oxygen, each oxygen is a -2 or 2-, and nitrogen must be 2+ because the total has to be 0. But if you have an NO2, and you have 2 oxygens, each oxygen is -2, that totals to -4 or 4 negatives, then nitrogen must be 4+. Oxidation number, it can go from group number to the minus of the group number. So if nitrogen is in group 5, oxidation number could vary anywhere from +5 to -5, but if you find oxidation number for nitrogen 6, something wrong. You have to check your calculation again. So allowed number is the group number to the minus of the group number. But group 7, always -1, unless they are dealing with another element from the group 7. And then you have the group 6, it could be -2, but it's anywhere from +6 to -6 is allowed, but these are common charges for these. Okay, let's see. These are some of the example. Oxidation half. When you write oxidation half, electron appears on the product side. When you write reduction half, electrons appear on the reactant side because your element or ion is gaining electron in reduction. So gaining electron means that electron has been consumed and is not a product, so it has to be on the reactant side. So if you see half a reaction that electron appears on the reactant side, that is a reduction half. With the overall reaction, the number of electrons must cancel each other. So you have to balance your equation in a way that, okay, how do we know an element is being oxidized or reduced? You just determine the oxidation number, like zinc here is solid. So any element in free state is going to be 0. So as a result, zinc is 0. On the product side, zinc has oxidation number of +2 because it's ion, and the oxidation number for ion equals the charge of the ion. What happens from reactant to product side? It goes from 0 to +2, that shows increase in oxidation number, and that's how we know that zinc has been oxidized. And on the other hand, for copper, you have a copper 2+, is going to copper 0. Going from 2+ to 0 is a decrease in the oxidation number or gaining of electron. Gaining of electron is reduction. Okay. Increasing strength as oxidizing agent, that means that zinc is more reactive than copper. Copper is more reactive than silver. So when we say reactivity for metal, that means how easy they can lose electron. They can lose electron. So it's silver is least reactive of all of these because it doesn't want to lose electron. It wants to gain electron, is least reactive. Zinc is most reactive because it wants to lose electron. It loses electron better or easier. Okay. Any questions about the part 1? Basically, you have the element and the ion metal. So you have the metal, and then you have the metal ion. Metal ion is the one that is in the solution, and metal is what you are adding, is a piece of copper, for example, or piece of zinc, or piece of magnesium. The one that is in the solution is going to be the metal ion. So if you have like a iron nitrate or any solutions that you have that has the ion, then it's going to be metal ion. And then you can check you basically check the video, look for observation, because if the reaction takes place, you have to look for evidence for the reaction. Evidences could be color change, or you would see like copper solid, like for this experiment, if the copper disappears, and then there would be color change, or if going from ion to free state, means you would see the particles of the red color or cupric color particles. Okay. Part 3, so this is the halogens. Is that the one that you had trouble with? Okay. When you watch the video, it might be easier. So basically, what you should compare in general, and when you watch the video, look for that. What is like if you have iodine in hexane, what color is it? Or if you have bromine in hexane, what color is it originally? And then you have to compare that to just the other point. You are looking for the color change, and also knowing that if this halogens, when they are in ion form, like if you have a bromide, iodide, or chloride, is going to dissolve in aqueous solution. But if they are in the molecular form, like I2, after they have been oxidized, or when iodide with a negative charge, when it loses electron, would change to I2. In free state, they are non-polar, so it will move up to the hexane layer. And then the color of the hexane layer is going to change. You may have to just go back and forth for that part of the experiment. Just look at the color of the iodine or bromine if it's just that element, that compound in free state. In the in hexane, and then when you have that inner reaction to see, is it going to come up to the hexane layer or is not going to come up to the hexane layer? I kind of emphasize, look, there is like a purple color. That means this element has been extracted into the hexane layer. But at the same time, I know that it's not very easy. And that's why I also added another video. This video, as I did explain to the class, that when I was doing the video, it was during the pandemic, and I was the only one in the lab, being cameraman, being the professor, being the student, being the lab tech, being everything. So, and I was using a laptop to record the experiment, which, you know, considering all this condition, I think that they actually came out to be very useful and very, very nice. But I didn't have someone to zoom in the test tubes. So on the other hand, we had another like 3 professors together, and they were doing, they were filming, and they only did 1 experiment for the entire semester. So if you watch the other one, no problem, Hannah. If you watch the other videos, is that there's more like zooming of the colors. You might see better because it's more zoomed in, and they were using the camera for the recording. So you can watch the other video also. It should be all the way down, and it says Professor Larry experiment 8. So there's video also, backup video as a resource. So you can use that also to watch it. It's going to help, but you have to go back and forth, and also know that what you are referencing is the color of each of this individual, like bromine or iodine, in hexane, and then the color when is in the aqueous solution format. So when you have a Ki, that means you have I minus, and then you have bromine. Bromine, if bromine is reduced, that means that I minus, which is iodide, is going to lose electron to bromine, is going to be I2, and then I2, it jumps or we extract it into the organic layer, which is the hexane layer. And the only way you could see it is based on the color change of the hexane layer. And many people, they have suggested to cut this experiment to make it like 2 experiments. So you do like parts 1 and 2 in 1 week, and then, but if we do that, then I have to skip another experiment, because we are, you know, we have to, let's say, not do experiment 10, but experiment 10 on its own is like it covers chapter of gases, so I don't want to skip it. So maybe I can do 1 semester, I could do like a part 1, 2, and 4, and then another semester do part 3 and 5, something in that nature, to reduce the volume of the work. But so far, you know, every class we have managed to present it, and students, they manage to either it's not good to say this, but you know, to learn or copy, one or the other. But I just hope that you understand at least 1 or 2 extra evidence, and your view of how to look for the result of the experiment being positive or negative. So if you know what you're looking for, it's going to make it easier for you. So hopefully when you're watching the video this time around, it would make more sense, and you can just go back and forth to watch it. I know you cannot fast forward for the when you're watching in the Blackboard, but I am moving everything to YouTube. Then you can go back and forth. At least you can rewind, or you can go back and forth. You just cannot fast forward this way, which is a good thing, except the parts that I have to go to the room to get more equipment or problems that happens. Okay. Questions for me? No questions? Okay. I'm going to take attendance this Friday and next Friday. We are interviewing for the college, and the interview starts at 9 o'clock. I'm going to hold the office hours. Last week I completely forgot because we had the interviews for other faculties, and this time I'm going to have the office hours, but it would be chat. I won't be able to use the mic during the meeting, and I try to, but if I see that it's necessary, then I have to quit, leave the other room and come to and answer your questions. So it's a good thing that it's because it's online, I can do at the same time. So I will have office hours this Friday. Okay. Attendance, Hannah. Hannah. Thank you. Sahir. Sonia. Ashley. Leah. Caitlin. Jennifer. Gret. Is Jennifer absent? I did get an email. So Carmen. Danielle. Davis. Caden. Suroti. Kate. Bianca. Bianca. Manisha. There was a message regarding someone. Okay. Jada. Jada, did I call your name already? No. Jose. Sierra. Javier. Lillian. Aisha. Matthew. And Ria. Okay, perfect. If you don't have any questions, you can start watching the video. It does help to watch, go back and forth, try to look at the color, record the color when you have the free state of halogens, especially. in the hexane layer or when you have them in the aqueous layer. So if the reduction takes place and the element changes to the diatomic molecule, when it comes to the hexane layer, make a note of the colors. So you have less of a problem because that's one evidence for the reaction. It says if I minus or iodide changes to I2, the only way that I could see in that reaction that it does change to the I2 is if I add a layer of organic solvent, because it's non-polar solvent. The reason we are adding hexane because it's a non-polar solvent, and halogens, if they are not in salt or in ionic compound, they as in form of the diatomic molecule, they are non-polar, and non-polar diatomic molecules would dissolve in the organic layer, which is a non-polar solvent. So in a reaction of, let's say, iodine with the copper, if iodide forms, I2 forms, it will go to the hexane layer. So kind of the evidences for part 3 and part 4, they are very similar. But if you go back and forth and just compare or take a screenshot and then just keep it what's happening in the next step, it does help you a lot with recognizing if there was a reaction or not. And from the activity series, you could also predict what should happen. Perfect. Thank you and have a nice day. It's a kind of a long experiment, so I saved you some time so you can start watching the video. Thank you. Thank you so much.